Well, great. Thanks a bunch for inviting me. As said, I'm Geoffrey Landis. I'm with the NASA John Glenn Research Center. I've been working on advanced technologies for future missions, but one that I'd like to talk about now is basically future missions to Venus and the possibility of human settlements in the Venus clouds. Let's see if I can get share screen to work. Okay. Okay, is that, see if that's sharing, and then, okay, which screen is that sharing? Is this sharing the presenter view, or is it the full screen?
Presenter view there, yes.
It's presenter screen, so I need to swap windows. How the heck do I do that? Swap windows. Oh, here it is. Okay. So how's that? So as I okay, that looks good.
No, now we see presenter view before we saw what we were supposed to see.
Oh, okay. It was wasn't the presenter view. It was the regular view. Okay. Yeah, the one has my notes and the one has. So
all good.
So as I said, I'm with NASA Glenn, and I just want to emphasize that this is a little bit more science fiction than NASA, but I'm going to try and cover both. So just an overview of where we are in the solar system. Here are the three inner rocky planets. Of course, we're all familiar with Earth. We've talked a lot about Mars, next planet out, about half the size of Earth, a little bit colder, a little bit thinner. But here's Venus. Venus is nearly Earth's twin in size. It's a little closer to the sun. This particular image actually is not what Venus would look like if you saw it with the naked eye. Venus is extremely boring when you see it with the naked eye. It is a featureless white ball. This particular image is what you would see if you had ultraviolet eyes. So you can see these markings, these dark ultraviolet absorbers in the clouds of Venus. But let's click through. This is what we'd see now if we could look through the clouds and look onto the surface. That color, JPL likes that color for maps of Venus. That's not actually what the color of the surface is, but it turns out the atmosphere of Venus is so thick that none of the blue light makes it to the surface. So only the orange and red light illuminates the surface. So it looks red, not like Mars, which actually is a red planet, but in this view, it looks red because the illumination on the surface is red illumination. Just comparing Venus and Earth, it gets a little bit more sunlight, a little bit lighter gravity, but an interesting fact is it's a very slow rotator. It takes 117 days, Earth days, for a solar day, and the atmosphere is 92 bars, where 1 bar is the atmospheric pressure at sea level on Earth. So it is a very high atmospheric pressure, almost entirely carbon dioxide. That makes it a tremendous challenge for exploration. The surface temperature is 452 C. That's the temperature in your oven when you're running the self-clean cycle. That 92 bar of pressure is the pressure a kilometer under the ocean. And just for making things equally hard, those pretty white clouds are concentrated sulfuric acid droplets. Like Earth, interestingly, the temperature drops as you get higher. I will talk quite a bit about this more, but as you go up from the surface, and you go through the haze layer, through the middle cloud layer, up to the top of the middle cloud layer, which is the thick cloud layer. Just about the top of the middle cloud layer, you're getting to reasonable temperatures. So that's a temperature of about 55 kilometers above the surface. I'll come back to this point a couple of times. But the surface here at temperatures of 450 degrees C is a very, very hostile environment. Another point about Venus is that the thick atmosphere and the circulation at the top of the cloud layer means that the temperature is very close to isothermal across the surface. There's no significant difference between daytime temperature and nighttime temperature, even though the nighttime is 60 days long. There's not much difference between the pole and the equator. It's all the same temperature, with the exception of as you go out to higher altitudes, it gets cooler. Lower altitudes, it gets warmer. Pretty much just like the planet Earth. Despite this, there have been missions to Jupiter. Missions to Venus. Sorry, I'm also working on Jupiter missions. This is the previous NASA mission to the atmosphere and surface of Venus, the Pioneer Venus mission, 1978. In fact, if you look at the picture here, there's an orbiter, but there was also a separate spacecraft that had 4 atmospheric probes, 3 little atmospheric probes and 1 big atmospheric probe that were designed to float down through the atmosphere and tell us what the atmosphere of Venus was like. And turns out, actually, they worked. 3 of the atmospheric probes made it all the way to the surface, so we've landed on the surface. 1 of the atmospheric probes broadcast for more than an hour from the surface of Venus. So we have landed and operated on the surface of Venus. Didn't have a camera. It was just designed to probe the atmosphere. But hey, we made it to the surface of Venus. But the real stars of Venus exploration has been the Soviet Union. And here's the Venera mission. These were great big stainless steel pressure vessels. So they survived the surface of Venus by the technique of just holding out the outside environment with a big rugged stainless steel ball. Here's a nice image I like. That's from Michael Carroll, showing that Venera lander on the surface of Venus. Record survival for the Venera was a little bit over 2 hours. So even with the big stainless steel pressure vessel, you don't stay operating on Venus for a terribly long time. Not the first one, but after a while, they started putting cameras on the Venera landers. Here are some of the early images of the surface of Venus. A couple of years later, some computer scientists actually cleaned up these images and took away some of the noise speckles and cleaned up. So here's a better view from the first landers on Venus. This is a Venera 9 lander. So we're seeing sort of a rocky, pebbly surface with some sort of regolith, some sort of dirt under the surface. Here's another one of these cleaned up images now, looking across a much more flatter plane for Venera 13. That's actually smooth as a lot of the parking lots that I've been on. This is a penetrometer over here designed to poke down and find out how hard the surface is. Here's another image, again, image processed by, in this case, by Don Mitchell. Couple of years later, they finally got some color pictures from the surface of Venus. Here's some of the very early color pictures. Again, here's Venera 14, where it's been reprocessed to add some detail on the surface. Well, the longest lived of these Venera probes was on the surface for less than, actually, say under, a little bit more than 2 hours before failure. We wouldn't have global maps of Venus except because we can't see it from above, but it turns out the atmosphere is transparent to radio waves. So the Venera surface was mapped by the Magella radar mapping. Here's a map of the whole surface in false color. They're, in this particular case, coloring the lowest areas blue, higher areas green, and then the very high altitude yellows and reds. So that's the Venus surface. Here's that same map of Venus now projected onto a sphere. So you can sort of see the sort of fantastic landforms of Venus, very interesting, enormously long lava flow features, that the lava has flowed in these rills, a lot of volcanoes. Very interesting image. Well, I talked about the surface missions. It is worth mentioning that the Russians also put a balloon mission into the atmosphere of Venus. 2 of the balloons floated at an altitude of 54 kilometers and stayed there for, well, they were tracked for 48 hours. After 48 hours, the wind blew the balloons around to the far side of the planet, so we could no longer track them from the Earth. Presumably, since they were battery powered, they didn't last too much longer. So we've put landers on Venus, we've had atmospheric probes, we've even had balloons on Venus, but the total amount of time on the surface is very short, cumulative times of only several missions with 2 hours of operation. A lot of what I've been looking at has been the question of what can we do for future missions to Venus. Here was one of my early proposals for a future mission, saying, well, can't we use what we have on Venus? What we've got on Venus is relatively light gravity, otherwise Earth-like, but above the clouds, we have a very Earth-like conditions. So why can't we fly a solar-powered airplane? Plenty of solar power, plenty of atmosphere to fly in. So we did a couple of designs of the solar-powered airplane. Here's the sort of the secret of getting the solar-powered airplane to fly is to put a lot of solar cells on the surface of the wing. So if we can fly on Earth, if we can find that same altitude where the atmospheric pressure is the same, we should be able to fly on the surface of Venus. So here's just some existence proof that we can fly on the surface of the Earth. Here's the AeroEnvironment high altitude Pathfinder airplane. I just like to show this one. This is a NASA Glenn solar powered airplane. But ultimately, we'd like to get down and actually look at the surface with rovers. Here is a study that we did of a Venus surface exploration. The difficulty is we need high temperature components. We need electronics, we need motors and actuators, we need material technology for extreme environments. Well, in fact, we're working on it. I like to show this slide. This slide actually is not colorized. That's a true color image. This is a silicon carbide light emitting diode that is glowing red hot. So the red you see is actually the glow from being inside the oven. But if you look very carefully, you can see that little blue light in the center. So here we're seeing a silicon carbide light emitting diode that's still operating, even though it's at a 600-degree temperature. There have been people who've been working at prototype high temperature motors, and they've been people even working on trying to design a power system for the surface of Venus. So far, this has been the hardest problem, trying to do a power system. We put all those together to get a surface rover concept. And maybe I'll see if I can get this movie to play. This is the rover concept that we came up with. The tricky part is we could come up with electronics that work on the surface of Venus, but they're very primitive electronics. They're about the electronics that we had. Oh, maybe that sound is a little bit loud. Let's see, is that a little bit less loud? So the electronics are relatively primitive. They're the era that we might have had in the 1960s. So we can have radio transmitters at low frequencies, but we don't have as computer chips. So the whole purpose of the mission was to design a mission to the surface of Venus that can operate on the surface without requiring computer chips. Well, we decided to use an ion engine vehicle to get to Venus. This was just because we had a nice design for that ion rocket that we wanted to use. Pretty fast to get to Venus. It's about a 5-month transit time. We come in, break to Venus, and then from Venus orbit, we get ready to drop down our descent probes. First descent probe separates from the carrier vehicle, uses the heat shield to enter into the atmosphere. And then, of course, we drop first a drogue chute, then a main parachute, and then we can deploy the solar-powered airplane. Okay, so the airplane flies above the thick cloud layer. And then once we have the airplane in stable flight, it can fly faster than the wind, so it can stay stationary over one spot on the surface. With the airplane down, we drop the next of our entry bodies. We have a starting parachute. We drop the heat shield free. Then we have a second parachute, a larger parachute to slow us down. And then the large parachute can drop our rovers down to the surface. Now, because we don't have sophisticated electronics, the rover is very simple. It has the electronics that can run the wheels. We have the high temperature motors, but it doesn't have an onboard computer. So instead, the overhead airplane serves as a relay, and all of the brains for the operation are in the airplane overhead. So the airplane has the computer that operates the rover on the surface of Venus. So this was our proposal for a Venus surface mission. Got a lot of interest, but unfortunately did not get the funding. We still have some technology development to do. That's maybe part of the process, but we think that it's feasible. We have the high temperature electronics. We should be able to make rovers for the surface of Venus. I think in the interest of time, I'll just move on to the next. I just want to show this image from Michael Carroll again. The reason I want to show it is if you look very carefully, you can see he put in the background, there's my rover, there's my Venus rover in the background of the image, getting ready to drive up and take a look at the Russian lander. But I've been talking about robotic missions. What I'd really like to do is send human missions to Venus. And in fact, the rover mission was intended to be nothing but a precursor to a mission with humans. Well, Venus is literally the hell planet. It is hotter than hell, it's a high pressure, and it is a corrosive environment. But it does get cooler with altitude. So somewhere around that 55, 57 kilometer altitude, we have that sweet spot, that 20 degree C altitude, and it's just above that thick cloud layer, the thick middle cloud deck. So the problem is not that it's too hot. The problem is if we define sea level as the point in the atmosphere where the pressure is Earth sea level pressure, the surface is just too far below sea level. So it brings the idea, well, why can't we put the humans in habitats, perhaps suspended below balloons that float in the atmosphere? Actually, a team at NASA Langley did a pretty detailed study of that. They said, well, we could do a habitat. We would have an airship and then even have a habitat where the humans could live, be quite comfortable at that 56, 57 kilometer altitude and explore Venus perhaps with remotely controlled rovers. Well, in fact, it's superior in some ways to other places that people have proposed space colonies. We're not in a vacuum, so that we don't have to live inside a pressure vessel. We talk about living on Mars, but the Mars pressure is less than 1% of Earth's atmospheric pressure. So the Mars habitat would have to be a pressure vessel. It would have to hold in atmospheric pressure. On Venus, you don't have to do that. You have to keep the atmosphere out, but you don't have to hold pressure behind it. The gravity is just about right. You'd lose a little weight moving to Venus. Most people would like that. We get radiation shielding from the thick atmosphere. So we're not getting a high radiation environment. And we have a lot of resources in the atmosphere. Pretty much everything you need is there in at least some quantity. We have, of course, carbon and oxygen in abundance. There's nitrogen in the atmosphere. Hydrogen's a little harder to find, but the sulfuric acid has 2 atoms of hydrogen per molecule of acid. So Venus is a nice place to live. The temperature is about right. So realistically, it is pretty much the most Earth-like environment in the solar system outside of Earth. So why don't we colonize Venus? Well, I was talking about habitats for humans, but we could float above that thick layer and make actually cities for humans. Turns out it's not hard to float on Venus. Air, ordinary breathing air, an oxygen-nitrogen mixture, is a lifting gas in a carbon dioxide atmosphere. It's about half as good as helium in lifting capability. Helium lifts about 1 kilogram per cubic meter of balloon. Oxygen and nitrogen in carbon dioxide lifts about 0.5 kilogram. Nevertheless, if you had a 400-meter envelope, you could lift 350,000 tons. So the nice thing about this is humans could then live inside that gas envelope. So the humans wouldn't be living suspended from a balloon. They would actually have the whole envelope of the balloon to live in. Here's one of my first images, sort of trying to envision a Venus city. Here's actually a book on a different subject, a science fiction novel that has a nice image by Don Dixon from the book, just showing what a Venus city might look like. Well, you do have to pick what altitude do you want. I've been talking about that like 56, 57 degree altitude. That gives you about the right temperature. Atmospheric pressure is a little bit over 0.5 bar, which means that if you have 37% oxygen in your mix, you get sea level breathability. You might want to go a little bit higher just to get into slightly cooler atmosphere in order to give you better heat rejection. But some people have come up with some quite fanciful images of what a Venus city might look like. But if we can do one city, why not many? You could do a few cities, you could do a lot of cities. In principle, with a surface area 3 times the land area of the Earth, you could put 10 million habitats in the atmosphere of Venus, each with a population of hundreds of thousands. So you could put a lot of people in the atmosphere of Venus. I have to say, when I first wrote a paper on this subject, I said, oh, we could put 1 billion habitats in the atmosphere of Venus. Well, turns out if you have air traffic control, you probably want a little bit more room between them. I just like to show this one. I do mention I am a science fiction writer in my spare time. This was a science fiction story I wrote about a habitat on Venus with another visualization of what the habitat on Venus might look like. Well, if you go beyond that, a lot of people are asking the question, well, can't we just terraform Venus? It's almost Earth-like. Can't we do something to get rid of that greenhouse effect and cool it down, make it livable? Well, terraforming was actually coined by science fiction author Jack Williamson, but the proposal to terraform Venus was first proposed by none other than Carl Sagan in 1961. So his proposal was pretty simple. He said, well, problem with Venus is the greenhouse effect. Why don't we just put photosynthetic bacteria into the atmosphere, have them convert that carbon dioxide to oxygen. They can release the graphite, the carbon, drop it down to the surface, and we get an oxygen atmosphere instead of carbon dioxide, and get rid of the greenhouse effect. Well, good idea, but eventually even Carl Sagan realized, no, doesn't quite work. Back then, he knew Venus had a thick atmosphere. They didn't know quite how thick it was. At 90 bars, it's so thick that even if you could convert it into oxygen instead of carbon dioxide, you'd have an atmosphere of 65 atmospheres of pure oxygen. Pretty much anything exposed to that would burst into flames. But long ago, the graphite would spontaneously turn back into carbon dioxide, so it would short circuit the process. It's harder than you think. Well, problem with terraforming Venus is it has way too much atmosphere. In fact, it has 500 quadrillion tons of excess atmosphere. That's a number so large, it's really sort of hard to deal with. So how would you get rid of 500 quadrillion tons? Well, the first thought is, why don't we just blast it away? Well, we could use, what, asteroids, if we have enough asteroid impacts? Well, about the best you can do with an asteroid impact is an asteroid could remove all of the atmosphere all the way to the horizon. Well, if you did that, you can do a calculation. It would take about 2 million asteroids, 1 kilometer in diameter, or about 2,000 10-kilometer asteroids. I actually think by the time we have the technology to move asteroids around by the thousands, we'll probably have other uses for them than crashing them into Venus. Well, what if we do the same thing the Earth did? Earth got rid of its carbon dioxide. It got rid of it by turning the carbon dioxide into carbonate rock. Well, to do that, we'd have to pulverize the surface to a depth of about 1 kilometer, and we need a technique for producing those carbonates. On Earth, we need water to do that. We dissolve the carbon dioxide to form carbonic acid in water, and then that's reprecipitated out as calcium and magnesium carbonates. But on Venus, if we tried to do that, they decompose back into rock and carbon dioxide. So it's a very tricky process. So far, we don't have good ideas for how to terraform Venus. We could convert that carbon dioxide to something else, but it's a hard problem. What else would we convert it to? Final proposal, I think Paul Birch invented this first, is he said, well, why not just put a giant parasol in front of the sun, block all of the solar radiation to Venus, and just freeze that atmosphere? Well, even so, it takes a long time to cool the planet because it's a very high heat capacity. And in the end, you get a planet covered with carbon dioxide snow. Hard to figure if that's really a terraformed planet. So the answer to the question, can we terraform Venus, is pretty much, well, maybe, but it's pretty hard. One more thing you could do is perhaps give it life, but without actually terraforming it, not making it Earth-like, but keeping it Venus-like. So you could put plants in the atmosphere that could actually float in the atmosphere. Kelp is an example of a plant that uses bladders to float, well, in this case, in the Earth's ocean, but you could make larger bladders. Here's another organism. This is a Portuguese man-of-war. It floats in the ocean, again, with a large air-filled bladder. So potentially, you could be a habitat for life that's bioengineered to live on Venus. Well, more challenges to terraforming Venus that I haven't even thought about. Tough project, but possibly not impossible for a future technology. Well, that was a quick sort of lightning run through some of the concepts of what we can do with Venus. Just conclusions, it's in many ways the most Earth-like planet in the solar system. It's a tough challenge, but not necessarily impossible. And it's ideal in temperature and pressure for human life. So we talked about space colonization. Well, let's colonize Venus. Thank you. Let's see.
It's very inspiring and awesome to hear everything you're pioneering there. Sounds like it might be more feasible to just terraform the upper cloud layer and atmosphere for now, maybe.
Yeah, that's mostly what I'm thinking. The lower part is terrifically hostile environment.
Feel free to ask any questions, share your video.
Yeah, I was running through that pretty fast because you wanted me to leave time for questions.
Thank you for such a thought-provoking presentation. This is the first time I'm seeing floating cities, and I have two questions. One, the first one is basically my survival instinct. I'm seeing a city and I'm thinking something will go wrong and it will fall down and people will boil to death.
Mm-hmm.
So what are the backup options for the cities so they don't crash and kill everyone? And the second question is related to funding and your feasibility. If you have parts of the project, such as the plane that's solar powered, have you considered validating parts of your project somewhere else, such as on the moon or on Mars?
Yes, absolutely. You have to build up from small to big. You're not going to move right immediately to the floating cities. Yes, people would of course worry very much about what happens if you have a problem. I think it's a solvable problem. We do live with technology, of course, every day. We are dependent on technology just for things like giving us our food and water supply, much less doing things like flying an aircraft at 500 miles an hour at altitudes of 7 miles above the surface. So we know what it's like to be dependent on technology. The nice thing about the Venus habitats is that they aren't holding pressure. So if you were to, for example, break a hole in part of the membrane, the air wouldn't leak out very fast because there's no pressure to drive the air out. The pressure on the inside is the same as the pressure on the outside. But nevertheless, you would definitely want to have some backup capability. You'd want to have not just one balloon. You'd want to have actually.
It looks like lots of duct tape, just like on ISS.
Yes, it would look like probably like a cluster of grapes. So you'd have lots and lots and lots of balloons. I should probably find a good picture of that. Lots of balloons. I'm zooming over to image search just as soon as I hang up here and find a good picture of that. But it would be a cluster of balloons, so that if you lose any one of the balloons that are holding you up, you wouldn't be destroyed.
And how about the other part of the questions for validating parts of your project, such as the plane somewhere else, where there is actually more funding and more commercial interest in the short term?
Well, there's a lot of people that are interested in solar airplanes for Earth. When I first started this, you could count them all. You could name all the solar airplanes, and now there's so many, Solar Zephyr and all the others. So each one of those is validating a technology for us. The tricky part actually is sort of folding it up so that you can drop it in an aeroshell and have it all deploy. The interesting thing is there was a Mars airplane project back quite a few years ago now that actually demonstrated that. They took their prototype Mars airplane up in a high altitude balloon. They took it up to an altitude of, I think, about 35 kilometers and dropped it from the balloon. and had it unfold as it dropped and come out and then transition into level flight. So parts of it actually have been demonstrated. Unfortunately, they never got the funding to fly it to Mars. They were a proposal for a discovery mission, but they didn't win the proposal. So we have not had a airplane on Mars, but now we have a helicopter on Mars. So next best thing.
Maybe we just need to wait because like Elon Musk is very interested in Mars, and he has technologies that are solar technologies. So maybe it's just a question of time before he starts having solar planes. If he thinks that's viable, because I think he's particular about what he likes.
Maybe I should write him a letter.
Maybe.
The other place that's beautiful to fly on is Titan. Titan's great for balloons. It's great for powered aircraft. And of course, actually, there's an octocopter that's going to be sent to Titan in a few years. So it's, I'd love to get my hands on the controls of that or design my own airplane for Titan. I wonder if I could hitchhike and send one of my airplanes to Titan.
Awesome, thank you. I will give space to others to ask questions too.
Geoffrey, sorry, it's Terry Trevino here in San Francisco. Martina, always good to see your wonderful smile. You're amazing. It's really good. Cole, thank you for piecing this together. Geoffrey, I'm really keen on knowing more about, I guess it was 2019 when we heard about a little known chemical that no one knew about. It was all of a sudden discovered, and now that, you know, it's, I guess Dr. Greaves kind of been maybe debunked a little, although it sounds to me like she's still looking.
Yeah. So the discovery was of the molecule phosphine at parts per million levels in the atmosphere of Venus. The discovery was by spectroscopy all the way from Earth. So telescopes doing spectroscopic analysis of the upper atmosphere.
And old images.
Yeah. And that's still a very controversial issue. Some people say, well, no, that's a high, not a very good signal to noise ratio, that we can't really be sure that it's there. We need a better signal. So maybe. Other people are saying, no, it's a different chemical. We can't be sure that the chemical we're looking at is actually phosphine.
Yeah,
and then the question of,
you're right. Yeah, when you look at her paper, it's not very clear, even in the paper.
Yeah, but you use the word debunked, and it isn't quite debunked.
Not yet.
It's the question that says we need more data before we believe this. That's sort of you can't say yes, you can't say no. But fortunately, there's a couple of missions that are already on the books, including an MIT mission.
That's right.
A private MIT, well, it actually Rocket Lab is funding a mission to Venus.
Yeah.
So we may learn a lot more if we can, once some of these missions fly.
And isn't one of our probes flying by here in the next few weeks or months, and we're supposed to get some more data, hopefully. I just kind of remember, maybe it was Osiris or
Osiris.
Osiris Rex.
Osiris Rex is coming home.
Somebody is flying back by with an extended mission, and I can't remember. I just remember thinking, oh, it's a great opportunity. Maybe it was PSP. I don't know.
Yeah.
It seems to be flying by too fast.
Yeah. Parker Solar Probe makes repeated Venus flybys. Not really designed to look at Venus, but of course, it's got the instruments it's got. Unfortunately, what it doesn't have is the type of spectroscopy that would look at the phosphine in the atmosphere.
Copy that. Well, it's by the way, good to meet you. Finally, over the years, I've heard you. So nice to meet you.
Yeah,
anyway,
Venus.
I'll be quiet. Everybody else can speak. Sorry.
Yeah, Venus is a good temporary stop by point for a lot of probes. A lot of people go by Venus on the way on the way somewhere out.
Copy that.
Awesome. It sounds like Venus could be easier than Mars, but we're
In some ways, yeah.
wondering if tethering and forming the clusters of balloons would be challenging with the high 355 kilometer per hour wind speeds.
Yeah, probably. There was the one image that showed sort of several of the fanciful concepts tethered together. That might end up being hard. There is some amount of wind shear and turbulence. I'm thinking the vehicles would be large enough that the turbulence would be kind of averaged out. You wouldn't get them bouncing around. But if you had multiple habitats kind of tethered together, well, the wind shear is going to try to pull them apart. So more likely they'd want to be independently floating.
And we're also curious if it makes more sense for the vertical transport of cargo to be like not opposed to the wind forces. If that makes sense, like in line with the direction of the wind, or if it doesn't matter with these tethered clusters.
Yeah, you are going to sometimes want to go down to the surface, both to do science, but also there's probably resources you need on the surface that you might want to go all the way down to the surface for. Although it's amazing how much you can do with just carbon, hydrogen, oxygen, nitrogen, and a little bit of sulfur. You can put together plastics, you can put together graphene, carbon, all sorts of things. But you probably are going to sometimes want to dip down to the surface to gather resources that you need from the surface. The two choices are to basically sort of make an aircraft that can descend down to the surface and then lift off again. Probably not impossible. The other thought, which would be much more difficult, would be to actually lower a tether down to the surface. So you'd need a tether that's, well, if it went straight down, it would be 56 or 60 kilometers long. But of course, because your city is moving, it would probably drag across the surface. That might be more difficult. You'd probably end up doing both, actually. So you'd have a tether that drops down into the middle atmosphere and then use that as the base for a balloon that could go down to the surface, grab your samples, and then go up to the tether level.
I have a quick question. Can you hear me?
Yes, I can.
Okay, great. This may be out of the scope of this particular project or this particular presentation, but just curious because I'm more in the medical field. Has there been any studies or anything done to test or know the effects of being in Venus on the human body, the effects of how the human body may react to the atmosphere of Venus? Such as, they've done multitudes of studies over the years of how microgravity and how the body reacts over long term with the astronauts going to the International Space Station. And they've even done, thoughts about how Mars would react towards the human body. But I'm just curious about Venus. And then also, you might have mentioned this already, but what's the gravitational pull compared to the Earth that's on Venus and how that might affect the body? If you know the answer, if there's studies that have been done.
No, actually, biology is always something that we need to know more about. The gravity pull on Venus is only a little bit less than Earth. Earth is 9.81 meters per second squared. Venus is 8.87. So 10% less, give or take. So probably the gravity won't be a big deal. The effect of low gravity and microgravity on humans, we're just beginning to learn the microgravity effects, and most of them are pretty bad. But nobody really knows what the minimum value to keep humans healthy and happy and keep their bones from demineralizing is. We don't know what would happen if people tried to live on the moon for a long period of time. There are a lot of the Mars advocates conjecture that Mars would be okay. It has about a third of the Earth's gravity, but we don't know that. So if you're advocating for biology experiments, a really, really valuable experiment would be to do a variable gravity research facility. We can simulate gravity with centrifugal force easily enough. It would be possible to put together a variable gravity facility, but it would answer a lot of questions that we just do not know the answer to. Venus is probably not a big problem. I'm thinking that humans are tolerant enough to changes in environment that the 10% lower gravity is not going to be a big deal. Another sort of interesting thing that affects humans is circadian rhythms. With that 117-day day-night cycle, you're really going to have to not live with natural sunlight, but have good artificial illumination for your circadian rhythms. But people live in Antarctica, so it's certainly possible to get used to the non-24-hour cycle.
There's also another data gap and knowledge gap. With the hydrogen and in situ collection, we've read over some literature on this 4e to the 15 kilograms as vapor, as water vapor in the atmosphere, around 0.002%. We're wondering, if this is actually potentially a lot, and if we could just filter it in and collect it with an atmospheric ISAP demo and collection unit.
Well, I would like to see the design for that unit. I've been assuming that you fractionate the water off of sulfuric acid. So if you have H2SO4 and remove one H2O, you get SO3. So you're splitting the water off and leaving sulfur trioxide out. But if in fact you could take the very low concentration of water in the atmosphere and nevertheless condense that out, well, that would be simple. Mostly my thought is, wow, that's a pretty low concentration. You've got to process a lot of atmosphere to get just a little bit of water. But with that said, we mine for a lot of things that are very low, very low parts per million. So if you can come up with a good design to do that, I would absolutely love to see it.
Cool, awesome.
I'm so curious, what would the travel between Venus and Earth look like? In particular, the return from the cloud city. Like, did you envision that we would have something like space station rotating around Venus, and that somehow there would be some kind of launch vehicle between the cloud cities and the space station, and then we would have another vehicle between space station and Earth space station?
Yes, that is exactly how I would do it. Launching from the atmosphere of Venus is not quite as hard as launching to orbit from the surface of the Earth, because it is a lower gravity well. Not a heck of a lot lower, but low enough to make a difference, remembering that the rocket equation is exponential. So you could probably put single stage to orbit vehicles, floating them in the atmosphere of Venus, but they wouldn't be little. This is not going to be a tiny thing. It won't be quite as big as a launch vehicle from the Earth, but pretty close. You really wouldn't want to launch from the atmosphere of Venus something that could take you all the way to Earth. So you'd want to stash your Earth routine vehicle in orbit around Venus. I would probably like to go with some sort of ion engines for it, some high specific impulse propulsion system. But with that, I have to admit, I haven't done the analysis on that part of the mission. I'm thinking, well, the transport system is something somebody else can worry about.
Right. And then somebody needs to worry about health, because some of the workshops I attended were hypothesizing that the other planets would adjust humans in a way that they may not be able to return permanently to Earth. So
Yeah.
that's another open question. So it would depend how long they were on Venus and what kind of adjustments can they do, and if they can even return without well surviving.
That's the one where I think Venus really has the great advantage, because it really seriously is the most Earth-like environment in the solar system. You can't go anywhere else and get that that gravity level and that atmospheric pressure level.
So I'm curious what other ISRU demos would be beneficial to propose and conduct. And, lightweight, sub, I don't know, like 5 to 10 kilograms. There's so many systems and data. It's curious. Yes.
Well, the ISRU for Venus, curiously enough, is going to start out looking very similar to ISRU for Mars, because the most abundant resource on Venus is similar to the abundant resource on Mars, the carbon dioxide atmosphere. So we already flew our first ISRU demonstration to Mars, the MOXIE, the Mars oxygen generation system that flew to Mars with Curiosity, and has demonstrated that we know how to make oxygen out of the carbon dioxide system of Mars. So if I were looking for stepping stones that go from where we are now to in situ resource utilization at Venus, the very first thing I'd do is build a bigger and better version of MOXIE. Ultimately, you could build a version of MOXIE that was big enough to actually provide the fuel for a launch vehicle that could launch you from the surface of Mars. So if we're going to explore space, we've got to start using those resources. We can't bring everything from Earth. Like Mars, we could also probably do the Sabatier process to make methane oxygen fuel. So there we'd want to pull the hydrogen off of sulfuric acid, or as you suggest, condense water out of the atmosphere to get hydrogen. And then by basically heating and with a catalyst, we can take that with carbon dioxide and turn it into methane and oxygen. So that would probably be the next step, because the very first thing you need for in situ resource for space is always rocket fuel, because rocket fuel gets you where you're going. That takes a lot of rocket fuel to go anywhere. So in terms of what you were suggesting, stepping stones to living on Venus, those would be the first 2 stepping stones: making oxygen, making methane. Beyond that, it would be interesting to try to learn if you can make plastics from the constituents of Venus. It would be nice if you could learn to make Teflon, actually. For that, you're going to have to, there is some amount of fluorine and chlorine in the atmosphere, relatively small amount, but Teflon, of course, is a fluorinated hydrocarbon, so you need to get some of the fluorine out of the atmosphere. But the nice thing about Teflon is it's resistant to sulfuric acid. So I foresee a big future for Teflon if we go to Venus. Everything wants to be Teflon coated.
Outstanding. We're also very curious if you or someone else, and who would be a good PI for a proposal with NASA, and but within the next 5 years or so.
The really good PIs are people with a burning science interest, but also a good engineering background. So, you know, sort of look around for Venus scientists who really understand the engineering. Well, not sure. There's a lot of good Venus scientists out there. They've been sort of disgruntled in the last 20 years because of the lack of missions to Venus, but they're all very happy now because people are talking about new missions to Venus. I might suggest Sarah Seeger of MIT, for example, who is working on the Rocket Lab mission to Venus. She's sharp. She knows what she's doing. She knows the engineering, and she's interested in the science. But people like that, people with a solid background in planetary science, able to follow the engineering.
Well, we can try to put together some research and over the years and try to support a proposal or something. I feel like we've the past 50 years, you know, since the 70s, we've kind of really been focused on the rocky bodies and the moon and Mars, and Venus hasn't been quite forefront.
Yeah, Venus has been the neglected planet, all right, but maybe we're changing that now.
Yeah, I think really thanks to you and all the amazing work you've done, Dr. Landis. I kind of lean more toward Venus than Mars these days, and I think it's awesome to see what you're doing. So.
Well, there's a lot to learn about Venus. We want to know why it is so different from Earth, and there's a lot of hypotheses about why it's so different, but we don't really know.
Do you have any specific next step you plan on taking, maybe in the short run or mid-run, to move this forward?
Oh, what are the steps that I'm taking? Well,
Yeah.
a number of them. We're mostly looking at this electronic technology for the surface of Venus, trying to get all of the pieces together to send a probe down to the surface that will last more than 2 hours. So there's a group at NASA Glenn, not my group, different group, that's working on the silicon carbide electronics. My group is trying to get a camera, a high temperature camera that will work on the surface of Venus. We're also trying to design a mission, sort of a low cost demonstrator that can go down to the surface and just show that it works. Just show we can get to the surface of Venus and operate. There's an interesting question, could we also do science if we did that? So we're looking at what science can we do on the surface? Very lightweight and very low cost. And one of the things we're thinking of trying to demonstrate on Venus is the seismograph. Find out if there's Venus quakes like there's earthquakes. That would tell us a lot about Venus if we could discover Venus quakes.
Have you considered proving the concept by making something like a mini city with maybe little rest or mice?
Oh, yeah, absolutely. Atmospheric platforms are high on my list of things to do as well. There was a group, a collaboration led by JPL looking at atmospheric platforms, and we were talking about airplanes, we were talking about variable volume balloons, fixed volume balloons, and right now they're very interested in designing balloon platforms for Venus that have the ability to change their internal pressure so that they can actually move up and down at will in the atmosphere. So I'm hoping that this technology will get mature enough that on one of the future missions to Venus, you can have just sort of a ride along of a technology demonstration, and we can put a demonstration platform in the atmosphere of Venus.
Yeah, so it looks like it will have to be a bunch of public-private partnerships and not like one company doing something big, but maybe more companies collaborating.
Yeah, especially if you can figure out ways to start small. It seems all of the big things in the world always started from a very little demonstration and then slowly get bigger. Very few things start out big.
Some, yeah, just about on the hour, but thanks so much, Dr. Landis, for your time here.
Okay, well, thank you for inviting me. I always like to talk about Venus and the other planets that we're working on.
Yeah.
So I'm glad to hear things are going well over on your side of things. So keep up the good work.
Likewise. Hopefully we can invite you to give a lecture sometime with our students on the road.
Okay. Well, sounds like that's signing off. So I guess I'll wave goodbye to everybody and say it's been a good meeting. Thanks.
Thank you.